Problem number 2, count the number of multiplications. Yeah. To do that, yeah. So let us just, actually we did part of it, right? Remember, we already calculate number of multiplication for each term. So for this term, we did last time, yeah. The answer, we have the answer, all right? Yeah, K is the answer, yeah. And remember at that time, we apply the strategy, try simple examples, yeah. So we find this answer, yeah. Now, we want to accumulate the total number of multiplications for the whole polynomial. Yeah. Let us do a chart here. Yeah. Yeah. First, yeah, A0, that term, no multiplication. Yeah. After that, A1x, 1 multiplication. A2, x squared, 2, and so on. If we add up all these multiplications using this simple formula, yeah, I think every one of you know this formula, right? Yeah, from your discrete math, yeah, summation formula. This is a very simple summation formula, yeah. So with this answer, this is our final answer, yeah. Then remember, we need to convert to the number of time units. We know each multiplication, based on our assumption, it has 10 time units. So let us do that conversion. We just multiply 10 to this formula, yeah. And after a little simplification, we get this expression as the total number of multiplications. Yeah. All right, so we find the answer. Yeah. But after we find the answer, the first question, yeah, when we work on algorithm problem, every time after we find one solution, we always need to ask ourselves, can we improve our algorithm? Yes. Yeah. At least you need to think about this question. So here, we raise this question, how to reduce this number? At least we need to make some effort to reduce this number. Okay? Yeah. We need to try it. Yeah. So the next question we need to do. All right, yeah, we try to reduce that total number, time units, that expression, 5n squared plus 6n. Can we do better than this? Yeah. All right. Improvement strategy. Now, we need to apply some strategy. At this point, most of us may not have an idea on this question. Yeah. So let's try to do some important observation. When we work on the problem, observation is always important. Observation. We examine our problem carefully. So what is the goal of observation? What is the goal of observation? Yeah, here, let me write down as simple as this. Find a key property. Key property. Yeah. At this point, we don't know that, right? We don't know what is the key property of this problem here. So we need to examine the formula of our polynomial and see what kind of property we can find. All right? Yeah. All right, first, cost ratio. Yeah, I put this factor here because this factor will impact our decision later. Yeah. The unit cost ratio, here the cost, execution time, we treat it as the cost we need to pay, right? We need to spend this much time. Yeah. Although not money, but time is also important, right? So we spend a lot of time, we treat that as our cost. So unit cost for multiplication over unit cost for addition equals 10:1 ratio. Yeah. So now let us do the thinking. Yeah. Our goal, we want to reduce the number of time units. Yeah. Here, the question, the first question, thinking, what the question? When we have limited amount of fund, here I talk about money again. Here I just try to, inspire you on thinking. When we have limited amount of fund, where should we put our investment? Yeah, this question connects to your real life experience. Real life experience. Yeah. All right. Based on your real life experience, try to think about this question. All right. Yeah. Okay. Invest here. Look at this. If this is the right way to do, invest the more rewarding part. Yeah. Think about if you have several places you can put your investment, which part you should place your investment. Yeah. The most rewarding part, right? The most rewarding part. Yeah. Here, let's look at here. We have two parts, multiplication part and addition part. Okay. Yeah. M part and A part. Multiplication part and addition part. Which part is more rewarding? Think about that question. Yeah. Which part is more rewarding? All right. Yeah. So let me show you our original formula, this expression, and let's look at the contribution of two operations. The first term is the addition contribution. The second term, that is the multiplication contribution. Okay, yeah. Here, when we make our decision, we have two options for our decision. First one, try to reduce the number of additions. The second one, try to reduce the number of multiplications. Yeah. Which one is better? Which one is more rewarding? Yeah, this question. Yeah. All right. Think about for addition part, even if you do a great job, the most you can do are the most n additions, right? You can cut off at the most n additions, right? Yeah. You cut off all the additions, cut off at the most, reduce at the most n additions, right? Let's think in this way. Reduce at the most n additions. All right. Then let us look at the multiplication part. In this expression, how much room do we have if we want to reduce the number of multiplications? Think about that. Yeah, if we just make some modest assumption, is it possible we can reduce n squared multiplications? In that relatively big expression, if we just set our goal, modest goal, reduce n squared. That's possible, right? That's highly possible. You can see it can already beat addition side investment. Think about that. In other words, if we make our investment at the multiplication part, it is much more rewarding than we put our investment at the addition side. How about that? Think about this analysis. All right. So based on this analysis, then we can make our conclusion. Yeah. So here, yeah. For the addition part, much less room for improvement, right? Yeah. So little, the term value so small that corresponds to, that can be translated into, it has much less room for improvement. For the multiplication, yeah, more room for improvement. Yes, that's our conclusion. We focus more on multiplications, not addition. All right, yeah. So our strategy, here, let us set the strategy, reduce the number of multiplications. How about that? Yeah. So next, we will work with this strategy. Okay. All right. So next, B.3 topic, Horner's rule. This is the key solution part. Our final solution. Yeah, we will see the solution at this B.3 part. Yeah. All right, so let's start. This time the strategy. Yeah. Still, this effective strategy we used several times. Study a simpler case. Yeah. In order to reduce the number of multiplications, let us try a simple case first. Yeah. Let's work on n equals 2 case. Yeah. Not n equals 1, n equals 0, because if we look at n equals 1, 0, we cannot get anything useful. We cannot get anything useful, all right? Meaningless, yeah. So we should, yeah, in other words, when we try a simpler case, at least we need to try non-trivial case. Non-trivial case. Because if you try trivial case, you cannot get any useful information. Yeah. So n equals 2, that is our first non-trivial case. Yeah. So on this formula, let us do our observation. Yeah. So in the previous slide, I emphasized that observation is very important to find some key property. Yeah. Here we need that. Here we need to find the key property. Here, yeah. Let's take a look. So, what kind of property can you see looking at the last two terms? Can you see any special property here? Just look at the last two terms. Yeah. What property is there? Let me just point out, common factor x. There is a common factor x. That's the property. This property is important. If you find this property, we can take advantage of this property. So how do we take advantage of this property? Yeah. We can do factorization. Think about that, factorization. Yeah. This is the factorization, right? Yeah. So simple. Just factor x out. Yeah. But the question is, after we do the factorization, is there any difference regarding the number of multiplications? If we count the number of multiplications in this formula, after the factorization, before the factorization, is there any difference? Yeah. Before the factorization, yeah, I put this number 3. The first term has 1 multiplication. The second term has 2 multiplication. 1 plus 2, so we have 3 multiplications. Now let us look at the second expression, right-hand side expression. How many multiplications? 1 here, x times that parenthesis. We do not count addition. We do not count addition. And the second multiplication is here, a2 times x. You can see the total number of multiplications is 2. Yeah, right? Yeah, think about that. Yeah, it's so simple. Yeah, right? So simple. Yeah. Is that a significant gain? Yeah, think about this. This little change, we just do factorization. This factorization gives us some gain. What is the gain? Reduce the multiplication from 3 to 2. Is that significant? Think about this. Reduce the number from 3 to 2. Do you treat it as a significant improvement? Right? Only 1, but that 1 is 1/3 of the 3, right? But 1/2 of 2, 1/3 of 3, 1/3. It is quite significant, right? Think about when you make an investment, if you can get 1/3 of the gain, is that significant? That is very significant, right? Yes. So the significant gain tells us this is a successful experiment. Yes, we really get something important from this experiment. Yeah. Think about that. So we try to explore it. Yeah. This also tells us it is a promising way to go. We should along this way and continue on this direction to do more exploration. Yeah. All right. Yeah. So the question, can we generalize this idea to the general N? Yes, that's what we need to do, the general N. Yeah. All right. So here, before we do the generalization, so let me do some, summarize our investigation so far. Yeah. The essence of the strategy. Yeah. Here, our strategy is effective. Yeah. So the essence of this strategy, we just try a simple example. From a simple case, we may find some important property that is helpful for the general case. Yeah. When the case is simple, it is much easier to find a solution, right? To find a solution. Yeah. So after we find a solution, we can extract some important property in our solution. Yeah. Then we try to generalize the idea to the general case. Yeah. So that is the essence of the strategy. Study a simpler case. Yeah. All right. Then another thing, observation. Yeah. Yeah. All right. So another observation, useful observation in this slide, our successful experiment. We have this. Changing the structure of an expression. We're talking about this part because the factorization allows us change the structure of the expression. So changing the structure of an expression could reduce the number of certain operations. Or in general, we can say in this way, changing the structure of an operation could provide us some new property. How about that? Provide us some new property. The two expressions, they have the same value. Yeah, we do not change the value. Two expressions have the same value, but we have two different structures. So we also have different properties from different structures. Now, the new structure may provide us new property so that we can new outcome. Think about that. Yeah. New structure may provide us new property, and hopefully we can get a new outcome. Yeah. So the goal is we want to get a new outcome. In this example, we have a new outcome, right? The number of multiplications is greatly reduced. That's the new outcome. Yeah. All right. So that's the things we learned from this slide. Yeah. Let's go to the next slide. Yeah. All right. Yes. Yeah. I have also something useful. Formula transformation. Yeah. What we did, changing structure of an expression. Yeah. We also call it formula transformation. Yeah. This method later we will use it again and again. Formula transformation. Yes. Yeah. So here we have a successful example in formula transformation. Yeah. Next. Yeah. This time, now, we just did one simple example. Do you like to do another example to consolidate our finding before we push to the general case? Yeah, so probably sometimes in order to do verification, try another simple example to see if our method still works. So we can do another one. Yeah. So in this slide, let us try n equals 3. Yeah. All right. Yeah. So for this example, can we use our previous factorization method? Another simple example, n equals 3 in this polynomial. Yeah, it's a cubic polynomial. N equals 2, that's a quadratic polynomial. Can we apply our factorization method on this cubic polynomial? Yeah, it is. The degree is not high, so we should have confidence here. Yeah. Let us try. The factorization should cover as many terms as possible. Okay, yeah. Right, yes. So here, this is our, oh, I need to change the color of the pen. Every time I start a new presentation, I need to change the color. Yeah, yeah, because it's not a one-time change. Yeah. Yeah. So this decision is important. The factorization should cover as many terms as possible. This decision is important. Yeah. So let's look at that. Yeah, look at this factorization. Yeah. Because we cannot find a common factor for all 4 terms. We have 4 terms in this polynomial. But if we skip the first one, yeah, we do not consider the first term, A0, the constant term. We only look at the last 3 terms. Then we can find a common common factor, x. Yeah. Yeah, because we get a common factor for the last 3 terms, so we can factor it out and write it in a similar way as our previous one. That's this one. All right. Yeah. Okay. Yeah, that's a good extension, right? We extend our technique to n equals 3 case. Yeah. But after that factorization, can we do a little more? Yeah, this method works well. How about just try to do more this kind of factorization. Yeah. Because inside the parenthesis, we have another formula, right? Yes, a quadratic formula. Yeah. This quadratic formula similar to our n equals 2 case, right? N equals 2 case. Yeah. So can we repeat our factorization when n equals 2 inside this parenthesis? Yeah. Yeah, we can do. Yeah. So for the remaining terms, we can do the same kind of factorization using our old experience from n equals 2. Yeah. So the result is we have another round factorization inside the parenthesis. Yes. So you can see at the end, that is our new factorization. So you can see, working on another example, n equals 3, we have some new finding, right? This new finding can help us to do further extension, the general case extension. How about that? Yeah. So this kind of analysis, this kind of exploration, this kind of investigation, in your problem solving, if you can do things like this, that would be great. Then your problem solving skill capability will be stronger and stronger. Yeah. All right, let's continue. Yeah. The idea, when we move to our next step, go to the general case. So we need to have some good idea. So the summary of our experience so far, push this method to the general case. What do you mean, this method? The factorization method. Factorization method. We're talking about factorization method. Yeah. All right. So let us extend the pattern we found here. This is the pattern. Okay. The pattern we found here to the general case. Yeah. Okay. Yeah. All right. So let's move to our final round. Yeah. So final solution round. Yeah. Strategy. Yeah. For this generalization. Yeah. So here you can see why my first topic of this class, I talk about strategy and execution. You can see every time when we need to solve a new problem, we always start with strategy. Yeah. See. All right. So the strategy here, we use one sentence. Yeah. Do factorization as much as we can. Yeah. So I draw on the line below, as much as we can. That means this phrase is important in our strategy here. Yeah, it is important. Yeah. So why it is important? Yeah. So I need to give you a rationale. Yeah. I need to explain why it is so important here. Yeah. All right. Because this phrase corresponds to an important idea or method in algorithms, greedy idea. Greedy idea. Look at this word, greedy idea. Yeah. So it is borrowed from our real life experience. Yeah. So I don't know the author who invented this word in algorithms. Yeah. I mean, people sometimes they try to use some, special word. Yeah. All right. So here, this is one, greedy, because in real life, when we talk about people greedy on money, right? Try to get as much as they can on money. Yeah. But here we try to get as much as we can on algorithm improvement. Yeah, not the money. Yeah. algorithm improvement. It's a good thing. In algorithm context, it's a good thing. It's not a bad thing, right? So when you see greedy, so here it's not a bad thing. It's a good thing. It does not mean the greedy is a good thing. But another reason. I just give you my understanding. Another reason here. We know the greedy is not a good word. The greedy is not a good word in general, right? Here people use greedy here. I think the author probably has tried to convey another meaning here. That is, this method actually is not that good. This method has some big negative consequence. So we will see that later. It's another really good one. It has some, how do I say that? We will see later when we get more information. Let's talk about this one, good or bad again. All right, so here, that's our first view. Greedy algorithms. Yes. In our textbook, we have one chapter talk about greedy algorithms. But in this class, we have very limited amount of time. Probably we do not have enough time to cover that chapter. So here I give you brief introduction on greedy algorithms. So what's the greedy algorithms? We apply some property as much as we can at each step. That's the main idea of this algorithm. Here you can see as much as we can. That's the greedy part at each step. That's the way we apply the greedy algorithm. Two important parts. The greedy approach, as much as we can, that's the greedy approach. Then at each step, that's the local approach. Only locally. You apply the greedy approach locally, not globally. Yes. That's the reason I said there is some negative thing about the greedy algorithm. The algorithm may not be good because of this local approach. It may not be good. Yes. Let's look at the global approach. When we solve a problem in a global approach, then we should apply the property across multiple steps, not a single step. So greedy approach, single step. Apply some property at a single step, one by one, not crossing multiple steps. That's the reason it may not be good. That's the reason it may not be good. Okay, all right, So here, there is this kind of property. Local optimal solution may not be the global optimal solution. Yes, the greedy algorithm, we just try to get a local optimal solution. Each step, it's optimal. Because that's the best we can do. That means it's optimal. But if you put in the whole problem, if you consider all the steps together, then your final solution may not be optimal. So that's the reason this method, the creator of this method, just, implies that there is some negative consequence behind it, negative consequence. All right, beware of it. All right, But for this problem, we're lucky. When we apply greedy algorithm, we can get, I cannot say optimal solution. We can get extremely good solution. We can say that extremely good solution. All right, so let's continue. All right. Now the question, the general formula. This time, we have a lot of information in our mind. We have a lot of experience. We already worked the previous two simpler cases. So we have a lot of useful experience. We know this pattern, this factorization pattern, right? So when we work on the general polynomial, we try to do the factorization fitting in this pattern. How about that? Fitting in this pattern. Okay, yes, all right. How about this factor? Yeah, if I write it out, the factorization, that's the expression. How about that? Factorization level by level until we cannot do any more factorization at the end. That's it. You can treat it as greedy. We push our factorization thing to the extreme. To the extreme. You can treat it as some kind of greedy thing, but here it's a good thing. All right, it's a good thing. Yeah. So at the end, we get a nice factorization expression. How about that? Yeah. So this outcome, this final factorization expression, that is the famous Horner's rule. Very famous Horner's rule. Yeah. Pretty simple. Yeah. But the result, you will see the result is surprising. Surprising. How good. Here I cannot use words to express how good it is. How good it is. Okay? Yeah. Yeah. Let me show you how much we can get from this new factorization. Now, how many multiplications? Can you see how many multiplications here? Yeah. The number, let us count the number of multiplications in this new expression. Yeah. All right, yeah. So here, when we count, yeah, try yourself first. Anyone, if you try, can you type some simple answer at the chat area? If you get any idea, just type your answer. It's simple. It's a simple expression. Yeah. It's simple. Just type it at the chat area. So we can talk about that. Try yourself first. How many multiplications? Ignore the additions. Yeah. Do not count additions, only multiplications. Anyone want to try? Yeah. N minus 1. Good try. Yeah. First, good try. Yeah. I want to say it's a close answer. Your answer is very close. Close answer. Yeah. That's good. Yeah. When we are looking for our solution, we make many tries and we want to get closer and closer to the final solution. Yeah. Nobody can guarantee one try you get a final solution. Yeah. But we want to get closer and closer. Good. And I see answer N. Yeah, it's correct. It's correct. Yeah. Oh, yeah. But the important thing is, I want to ask you, when you get the correct answer, when you get correct, yeah, N is the correct answer. The thing is, what method do you use? Because the method is important. Correct method is important. Yeah, that will give us confidence. If you apply some good method, you will get confidence. Yeah, that is important. Yeah, so that's why I want to emphasize the right method to use in the step. Then after that, you won't ask me, is it correct or not, because you have a lot of confidence on your answer. Yeah. All right, so here, let me point out the correct method that we used before. It's not the first time we use it, the second time. Yeah, we already use it when we try to find the number of additions. Think about that. What method did we use when we count the number of additions? Counting by reference. How about that method? Counting by reference. Yeah. Here, when you count the number of multiplications, yeah, look at that. Each multiplication, x times that parenthesis, when you see that parenthesis, you may have one multiplication. Okay, left parenthesis, that's one multiplication. All right, yeah. Then you have another parenthesis between x and the second parenthesis, left parenthesis, another multiplication, and so on. All right. But there is a problem you need to overcome, dot, 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 dot. In that dot, dot, dot part, we skip many terms, a large number of terms. The question is, how do we keep track of the multiplications? It's hard to keep track of the multiplications, right? We get lost. How do we find some way to help us keep track of the number of multiplications? Find appropriate reference. All right, so here, can we associate the first left parenthesis to the first subscript A1, that one? Can we associate the second left parenthesis multiplication to the second subscript A2, that 2, and so on, right? The last multiplication, can we associate with the last subscript AN, sub n, that n? Yeah. So then, if you can find that kind of relationship, that kind of one-to-one relationship, one-to-one mapping. Yeah. So we have a good reference, subscripts as our reference, one-to-one mapping relationship. Then, when you count the number of multiplications, that is the same as counting number of subscripts in this list. 1, 2, 3, dot, 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 the last one, n. Can you keep track of these subscripts? It's very easy to keep track of, right? They are natural numbers. They are consecutive numbers from 1 through n. So you won't get lost, right? Nobody would get lost when they count the number of subscripts in the natural number list. 1, 2, 3 consecutive way through the last one, n. And in this way, you can be very confident that your answer is n. How about this method? Yeah, we apply it the second time. Yeah, I hope you get good impression here. So later in the future, when you have a similar situation, you remember to use this counting method. Very effective. All right, so we complete this slide and our solution. Yeah, we have really good progress. The final answer is n. Is n. How good it is. So small, right? So small. There, with this new answer, the last thing I want to do, how well is this, is our work? How good is our work? Yeah. How good is our work? Yeah. Our new solution. Yeah. All right. Yeah. Okay. Impact of the multiplication reduction. How big is the impact? Yeah. Think about that. Yeah. And we need to do visualization. We need to visualize the improvement. At this point, can you imagine how good is the improvement? You only know this is from the formula, you know, it's a big improvement, right? 1/2 times n times n plus 1 parenthesis from that expression to n. You know, it's big, but how big? Can you imagine that, how big it is? It's hard, right? Two expressions on paper, how can you imagine how much difference between them, right? Too abstract. Yeah. Here, the last thing I want to do in this part B is the visualization. Let you really see easily how big is the difference. I just try some examples, simple examples. At the end, you will see the difference is huge. Yeah. All right, so let's start our simple example here. Here I use two examples to visualize the improvement. Yeah. The first example, let us assume n equals 1,000. 1,000, the polynomial with degree 1,000. Yeah. How many multiplications do we need using these two methods? The brute force method and Horner's rule method. Yeah. All right. So let's plug in the numbers. Yeah. At the n side, just 1,000. At the expression side, approximately here, I do not use the exact number, approximate number. It should be good enough, right? Yeah. 500,000. 500,000 approximately. Okay. Yeah. So look at that, 500,000. Yeah. The ratio is 500 to 1 ratio. Is that big? Right? You make improvement. You only need to use 500th. Yeah. 500th, 1 over 500. 500th amount of time of the older method. How big it is. All right. That's our first example. But I want to try the second example. Yeah. When n equals 1 million. Why I look at the n number so big? Because look at our current stage in technology. We are in big data era, right? We are in big data era. At a big data era, the number of data items in the category of millions, is that strange or not? That's normal, right? Yeah, that's normal. The number of data items in the millions range, that's quite normal in the big data era, right? So it is very reasonable. We need to consider n equals 1 million situation. Yeah. So let's plug in these two numbers again and do the comparison. At the n side, just 1 million, same number, but at the expression sign, okay, look at that. Still approximate number, but good approximation. So we can look at how many zeros do we have. Can you tell us what is this number? Yeah, is everyone, you can tell how large is this number, right? Yeah, yeah. So from my side, it's 500 billions, right? 500 billions, that number. Yeah. 500 billion compared with 1 million, what's the ratio? What's the ratio there? Look at that. 500,000 to 1 ratio. Is that big? 500,000 to 1 ratio. Is that big? Right? Look at these two methods. The difference is huge. 500,000 to 1 ratio. Can you imagine that? Right? Yeah. But those two numbers I just put on paper, on screen, for you, still two numbers, right? Still two numbers, right? Think about, yeah. Some people have a lot of money in the bank, but the money in the bank is just a number, right? Can you feel about that? Yeah. If you do not spend the money, it is just a number there, right? Yeah. Here we have the similar situation. The number is on paper, on screen. Yeah. So we cannot feel it. We just feel, some digits on screen, right? Yeah. So here I need to find another way to let you feel about it. Let you feel about the big difference we have here on screen. Yeah. So let us do another experiment. Yeah. Here we add a time unit second. Yeah. So we make a story. Yeah. Here, when we try to visualize the difference of these two numbers, we make a story here. Yeah. So what is the story? Yeah. Imagine we apply these two algorithms to solve a real world problem. Yeah. The same problem. Find the value of a big polynomial with degree 1 million degree. Yeah. So you need to do the calculation and give me the answer. Yeah. That answer is extremely important because the new satellite relies on this number, to, fly to the space. Something like that, just a story, all right? Just, some story, all right? Yeah, just let you know, the answer is extremely important. You have to find it, all right? Now, you apply these two methods. Yeah. The second method, yeah, because we want to use the second method as the base. So we assume the second method can find the answer that corresponds to 1. So that 1, we assume 1 second. How about that? Yeah. 500,000 to 1. That 1, we treat it as 1 second. All right? Yeah. Yeah. Then at this 500,000 side, that is 500,000 seconds. How about that? Yeah. So if you use the brute force method, you need 500,000 seconds. If you use Horner's rule method, you need 1 second. That difference. All right. So now that number extremely important. You need to find it. All right. If you apply Horner's rule, 1 second, you get that correct answer. Now you use the brute force method. All right. Brute force method. You need 500,000 seconds. For how long is 500,000 seconds? Let us convert the time that we are familiar with in our everyday life. All right. Yeah. 500,000 seconds equals how many days? How many hours? How many days? Right? After conversion, you can do the calculation by yourself. Approximately 5.8 days. 5.8 days. So if you use the brute force method to do the calculation, you need to wait 5.8 days to get the correct answer. Then the new satellite has to wait for your number, yeah, because that parameter is important, enter into the computer of the satellite, and the satellite needs this number to, to get to the space station, things like that. Think about that. that kind of story. Okay, yeah. So that's the huge difference. Yeah. Now I think you can completely get an idea how big is the impact, right? Good algorithm, bad algorithm, how big is the impact? Okay, yeah. All right. Now we complete this problem, number one, evaluate a polynomial. So we find a solution. We find a good solution. And we do the comparison, and we know how good is the solution. Yeah. So now I can assign you project number one. In my project number one, we will do experiments on these two methods, brute force method and Horner's rule method. Because after you write programs, you do experiments, you will get your own experience about the big difference of these two methods. Any question, any comments so far? Yeah. We have only about 10 minutes. I do not plan to start a new topic. Yeah. Here, I just say a few words at the end regarding this result and related to our related to our first project, project number one, first programming project number one. Yeah. I plan to, let me see. Yeah. Today is, today is Tuesday, right? Yeah, Tuesday. Probably I can assign you the new project a little earlier. Yeah. Because you have all the background information already. Right? After this part B, you have the all the information already. Yes. So that we have an option. Remember our timeline, our schedule, timeline of the coursework. Yeah. So based on that timeline coursework, our programming project will be given next week, midpoint of the next week. Yeah. But I feel we are ready for the first programming project. So I may post it a little earlier. Yeah. So you have more time to work on it. Yeah. All right. So that's one thing. And in this programming project, actually, I will ask you to compare three methods. Yeah, not two, three methods. So why three, not two? Yeah, because when we use the brute force method, there are two ways to use. Yeah. One way, the first way, just what we did in this class, the current addition multiplication, the current way. Yeah. But the second way, yeah, it's also interesting to try the second way. Still, for the brute force, we apply existing function in the library, programming language, math library, right? Yeah, we can apply the power function. Yeah, so power function in library. Yeah. When we calculate a polynomial, we have many, x to the kth power, right? When we calculate x to the kth power, why just plug in the math power function directly? Do not do the normal multiplication. Power function directly. So that's our method number two. Now, you will see power function way will be much better than the direct multiplication way. Direct multiplication way is the worst. Then the power function weight is second. And the Horner's rule is the best. Yeah. All right. Yeah. So that's pretty much the information I like to give you related to our module 1 part B. And we finish our computing problem number 1, the solution. Yeah. And in our part C on Thursday, part C, I will start new topic, completely new topic. So that's why I do not want to start it today. Yeah. The new topic, we will study the impact of the data structure. Yeah. We know data structure is also very important in algorithm design. So we will have our view on data structure, in part C. Yeah. All right. Yeah. So that's it. Yeah. So if you have any question, you can ask me. So if you do not have any question, we can finish our meeting, our lecture today, right here. Yeah. All right. Good. Yeah. Yeah. All right. Yeah. The question. All good. Yeah. 2 questions. Yeah. Let me answer one by one. The easier one, do we need to get the book? Yeah. So my question is, that's your option. I do not require. So that's the first part. The second, my notes, if you follow my notes closely, it should be good enough. Yeah, but that's still your option. Only for some students, if you feel you need extra information, yeah, then you try to get a book. If you feel you just use my notes, but make sure you follow my notes closely, then yeah, I understand. Yeah, for some people it's very expensive. That's why I say it's optional. Yeah, but when I give you test questions, homework questions, I base on notes completely. All right, so you should be able to answer all the questions based on my notes. Yeah, so that's one question. Second question, will there be Canvas page for project 1 space? Yes, I will post project description as a PDF file. Yeah, so I create a project assignment. In my project assignment, I will post a PDF file as the project description. So I list all the requirement items, 1, 2, 3, 4, 5. So you just follow the instructions, requirements in my PDF file, project description PDF file. So then you can work on the project. Yeah. All right. Yeah. 2 questions. Yeah. The power function, is it algorithm? No, it's not an algorithm. Yeah. So let me get, so in Java, so for example, yeah, or in C++, yeah, I remember, so for example, POW parenthesis, yeah, AB, something like that, that equals the A to the B, yeah, something like that, yeah, something like that, yeah, that's the power function, yeah. No essay, the project, you do not need to write any essay, you just write your programs. I just look at your programs. I run your programs, and then I see the output of your programs. If you just follow the instructions of the project description, and I look at your output. Yeah, no essay. Yeah, you do not need to spend time, write essay. Yeah. Yeah. All right, good. Pretty good. Yeah.